title. This is going to be a summary, really, a little presentation about the Innovation Fund project that myself and Kim Gertz have been working on within the National Science Challenge, Sustainable Seas National Science Challenge. As already mentioned, I'm based here in Wellington, as was Kim. Kim's since left NIWA. She left NIWA quite recently and she's now back in the States. But a lot of the work that's being presented today is really down to Kim. So without any further ado, we'll dive in. The talk today is going to be following the flat structure that you can see, a little bit of background and context both for seabirds within New Zealand and the genesis of this particular project. I'll describe the approaches that we've adopted to explore the questions that we're particularly interested in, present some results, and finally draw one or two conclusions. Okay, so the background and context really in seabirds in New Zealand. I'm suspecting that some of these statements will be fairly familiar to some or many of you. New Zealand supports the most diverse seabird assemblage on Earth. At the last count, 168 species or subspecies have been recorded here in New Zealand waters. Of those 168, 99 breed in New Zealand, and of those, nearly half are endemic, which means that they don't breed anywhere else in the world. So New Zealand is really blessed with an extraordinary diversity of seabirds. Far more species and subspecies occur here than anywhere else, any other country. And many of those seabirds that occur in New Zealand have got a very high conservation status, and that generally means that they're classified as either threatened or at risk. And it would be fair to say that as well as being diverse, they're also relatively numerous, and they form conspicuous components of the marine environment. You could suggest also that they actually define the sort of marine character that we enjoy around New Zealand. It's a rare day when you look out to sea and you don't see a single seabird. So they're fairly conspicuous, they're numerous, and they're also very diverse. And just to re-emphasise that point about how numerous they are, this slide shows a couple of countries. On the left, you've got the UK, and a couple of other bits and pieces, and on the right, you've got New Zealand. And you can see from the bottom that the land area of those two countries is more or less the same. The number of seabirds that are supported in the United Kingdom in total is approximately, or perhaps even less actually, but on par with the number of seabirds that are supported on the Snares Islands. And the Snares Islands are, you can't even actually see them, they're so small on this particular scale, but if you see the red arrow on the New Zealand map on the right, it's pointing to where the Snares are, just southwest of Stewart Island. And there are probably more seabirds on the Snares than the entire UK. And you can imagine how many seabirds would have been in New Zealand prior to the arrival of two-legged and four-legged mammals. There are hardly any seabirds now breeding on the main two islands of New Zealand. One or two little remnant pockets of birds here and there, but generally they're devoid of breeding seabirds. But not very long ago, they would have been covered with seabirds as well. So whilst they're confined to the offshore islands these days, predator-free islands and so on, there was a time when more or less all New Zealand would have been covered in seabirds. And whilst those two land masses of those two countries are fairly similar, you'll notice that the EEZ areas are actually quite different. The EEZ for the UK, the full EEZ for the UK is much bigger than that, but for the EEZ was just around the actual UK that we consider there, just off northwest Europe, about 775,000 square kilometres. And New Zealand is much, much bigger, over 4 million square kilometres. Not only is it much larger, our EEZ in New Zealand encompasses a whole range of different habitats and environments, which has probably driven the diversity of seabirds that we see here today. You'll notice that around the UK, on that map, there isn't much submarine topography, quite shallow seas around the UK, far more diverse around New Zealand. And another sort of pretty self-evident fact really, that seabirds generally are very dynamic. They don't stay in one place, they move around. They can travel large distances relatively quickly, particularly the members of the Procellariiformes, which is the order which includes the albatrosses, like this white-headed albatross, petrels and the shearwaters. They're very efficient flyers, and they can travel relatively large distances relatively quickly and easily. So when these seabirds are breeding in New Zealand, it's not uncommon for them to forage and fly away from their breeding colony over the scale of the EEZ and even beyond. New Zealand breeding seabirds will often travel as far as Australia to feed and come back. And when they're non-breeding, when they're finished breeding, they travel even larger distances, often at the scale of an ocean basin. So, for example, sooty shearwaters, which breed in New Zealand, travel to the North Pacific when they complete their breeding cycle. And so, with that background of lots of seabirds, very high diversity of seabirds, one of the questions that is increasingly being asked in various fora is along the lines that's been highlighted here. So what will the effect be on seabirds of a proposed activity at a particular location in the marine environment? And that's the sort of question that is frequently asked in Environment Court hearings or EPA hearings when some applicant is wanting to do something, some activity in the marine environment, which could have an effect not only on seabirds but a whole range of other parts of the marine system as well. And the decision-making committees, as part of those hearing processes, end up having to deal with uncertainty. So in the case of seabirds, there's a level of uncertainty about which species occur where and when they occur where, and that causes issues in that sort of process. It's not a black and white situation at all. And you can imagine for species which are relatively sedentary, on the right-hand side there we've got a couple of Auckland Island shags. That's a threatened species in New Zealand, but it only breeds in the Auckland Islands. And it probably doesn't forage much more than about 20 or 25 kilometres from the shore. And so, at least theoretically, for sedentary species, that uncertainty could be reduced. But it's nevertheless true that for many species of seabird in New Zealand, we don't have good information about temporally resolved regional scale or sub-regional scale distributions. So that's the sort of temporal scale and spatial scale at which a lot of the activities that are either occurring or being proposed to occur in New Zealand waters operate at. And we need to sort of match up our information about seabirds to make reasonable comparisons about how those proposed activities could affect seabirds now and into the future. So that sort of question was really the background to the project. And traditionally and ideally, of course, what we need to know is where seabirds occur and how those distributions vary over time, at least seasonally. Not always possible, of course. And in order to gather that information, what we need, of course, is distribution data, distribution information, and those data are used to produce distribution maps that could be temporarily resolved. And again, traditionally, that sort of information is acquired from one of two sources. The sightings data, so this is observations of birds in the environment, at sea, of course, generally for seabirds or when they're breeding on land. And more recently, since about 1990, there's been a proliferation of miniaturized tracking devices, electronic tracking devices, which have been used to better understand the movements of seabirds at sea. So those two sources of information are generally the most commonly used when we're talking about distribution maps and how those distributions of seabirds change over time. So, for example, here's a couple of fairly recent cases where applicants have wanted to undertake activities in the marine environment. The smaller circle up there, just off the North Island, there's an application in that area to mine iron sand, and then there's an application across the Chatham Rise off to the east of New Zealand there to mine phosphate nodules. In order to answer questions about how those proposed activities might affect seabirds, we need site-specific seabird distribution information that's relevant to those two sites and those two scales. And traditionally, the way that would be done would be to undertake structured, temporarily resolved at-sea surveys of seabird numbers and distribution, and how that changes over time. And in order to do that, of course, you need to get on a boat, more than one person, and spend time zigzagging in a structured way across the area of interest on several occasions during the year, and ideally over more than 1 year. And it doesn't take too much imagination to realise that once you start chartering vessels, people's time on boats in those sorts of environments, that sort of exercise becomes staggeringly expensive very quickly. By contrast, tracking data, the other sort of information we can use to work out where birds go, in addition to saying where birds go, it also gives you information about the importance of sites relative to other sites that they may be using. And that's hard to understand if you're just in one site seeing which birds occur there on a boat. The tracking data allows you to analyse a number of sites that the birds might use and assign some importance to particular sites within that overall distribution. However, Tracking information tends to be limited to a relatively few individual birds at any one time, and often only from the breeding components of the population. So, back to the original sort of question, we adopted three methods really to sort of explore the validity and the sort of usefulness of these different methods in determining seabird distributions. And we employed the first method as a kind of unusual method in the seabird context. It's not really been applied to seabirds very much at all. I'm aware of one, perhaps two other studies, relative environmental suitability modelling. The second approach we used was using sightings data. And the third approach that we used, or compared with the other methods, was tracking data. I'll talk a little bit about those in turn, but just to say that the tracking data component we used kind of determine the species selection for the project. We used data that we had in-house, that we'd already collected. Some of it needed processing, but the availability of those tracking data determined the species that we chose to work on for the project. And it boiled down to these 5 species. So 4 albatross species, all of which breed in the subantarctic and the study shearwaters. So starting on the right-hand side, the Campbell albatross and the grey-headed albatross. As breeding species only breed in one place in New Zealand, that's Campbell Island. The white-capped albatross down there on bottom left also breeds in the subantarctic, but primarily at the Orkney Islands, a little bit further north. Southern Buller's albatross is another New Zealand endemic species found nowhere else on Earth as a breeding species. That species breeds at the Snares, the little red arrow that I showed you in that earlier plot, just off the southwest coast of Stewart Island. It also breeds on Solander Islands in Frobel Strait. And sooty shearwater is a little bit more widespread in its breeding distribution. It breeds as far south as Campbell Island and all the way as far north as the Three Kings. So it basically covers, as a breeding species, the entire latitudinal range of New Zealand. So for these 5 species, we had a reasonable amount of tracking data already collected. So they form the basis of the project. I won't be talking about all 5 species. I'll just be presenting some results from a couple of those. But those are the 5 that we used as part of the project. So first of all, relative environmental suitability modelling. So this is a fairly simple model. What the model does, it predicts the geographic range of a species of interest using basic descriptive environmental data. And the modelling approach relies on the generic relationships between species of interest and each of the environmental data layers that you choose to use. And those information about those environmental data layers is taken from existing sources. So these are just published papers, books, textbooks, manuscripts, wherever it might be, telling you about the relationship between your species of interest and a particular environmental driver or data. Importantly, for a model that's ostensibly trying to predict or describe the distribution of a particular species, the model does not incorporate any location information at all, which is kind of like counterintuitive. The model produces like a probability map of where a particular species might occur, but it doesn't actually include, as part of that modelling process, any location information at all. No tracking data, no sightings data. So it's a way really of producing a distribution map without knowing the distribution of the birds. Magic. And just a little bit more detail about the RAS modelling approach. So what the modelling is, a very simple model. We chose 3 environmental variables, and I'll explain why in a minute. But it basically it describes the relationship between the species of interest, in this case a bunch of seabirds, like that white-capped albatross on the right-hand side, and 3 environmental variables. And that relationship is described by that trapezoidal response curve that you can see in the plot. And it's only based on 4 parameters: min A, max A, min P, and max P. And min A and max A are the absolute minimum maximum variable values that a particular species will occur in. So, for example, sea surface temperature, some species will only occur or might only occur between an absolute lowest temperature and an absolute maximum temperature. And beyond that, they won't be expected to occur at all. And then within that absolute range, we have a preferred range, that's min p and max p. So these are the variable ranges that describe where that particular species would be most likely to occur or would prefer to occur. And then between those two, minimum absolute and minimum preferred, and likewise the maximum values, there's a simple decay function which goes from the preferred value down to the absolute value. So on the vertical axis there, that plot, probability of a species occurring goes from 0 to 1. So when you hit that minimum preferred habitat particular value, the probability of that species occurring at that location goes up to 1 and tends down to 0 as you approach the minimum absolute value. And so you combine information for the number of variables that you choose to use. Now for seabirds in New Zealand, it proved to be a tad tricky. And that's because there isn't really a massive amount of information about environmental variables which are good predictors of where seabirds occur over the ocean. It's very easy to come up with a whole raft, a whole suite of different environmental predictors, but without some information in the literature describing where particular species occur and the values for those particular environmental drivers, it's impossible to create these sort of models. So we had a longer list than this, but we ended up sort of falling back on 3 environmental variables: bathymetry, distance to land, and sea surface temperature. And what these plots show you are just sort of global climatologies, if you like, for those 3 variables. So on the top plot, we've got bathymetry. The darker shades of blue are the shallower parts of the ocean, and the colours which sort of tend to white are the very deep parts. And that middle plot of distance to land, the red areas are the places furthest from land. Conversely, the blue areas are relatively close to land. And in the bottom plot, we have a sort of annually averaged sea surface temperature distribution plot, which, not surprisingly, shows warm colours, those oranges and reds, towards the equator, tending towards colder temperatures towards the 2 poles. So, given those 3 distributions for those 3 variables, we trawled through the literature and found out a whole bunch of values for our 5 species of interest, and then layered those on top of each other effectively to come up with an overall probability distribution based on those 3 variables. And I'll show you the results of that a little bit later. Second approach, sightings data. So you can count on the fingers of one hand the number of structured at-sea surveys of seabirds in New Zealand. So for the 5 species that we were interested in, or which we had tracking data for, they didn't really sort of fall too heavily under any of those studies, so we fell back onto this, excuse me, this excellent web-based data portal, New Zealand eBird, which is a sightings database. People can submit their own sightings when they're travelling around the country or travelling at sea, and they become available for people to interrogate and explore. And it's a really fantastic website. I encourage you to use it. It's a source of lots and lots of really useful information. So the opening page is on the left of the website, and if you type in white-capped albatross, which is the species flying over the sea there, and zoom in onto New Zealand, you come up with that sort of plot, and those, if you make out the little purple boxes, are areas around New Zealand where sightings of white-capped albatross have been recorded, and the greyed out areas are places where sightings of seabirds at sea have been made, but there weren't any white-capped albatrosses in those places. And you can zoom in, and there's more detail underneath all those boxes and so on. So it was a source of lots of sightings data for all the 5 species that we were interested in. And finally, tracking data. So this is the data that we had in-house. Very briefly, tracking data comes in all shapes and sizes these days. Traditionally, for seabird work, there have been 3 methods developed. The first one, satellite data, known colloquially as platform transmitting terminal data. So these are things that you strap to the back of the bird, often taped. They transmit location information to an Argos satellite array. There are 7 satellites in that array, so not too many. The accuracy of locations at best is a little bit less than 250 meters. You typically acquire about 10 or 20 locations per day, not many more than that. The benefit of that approach, of course, is the data are transmitted from the tag via the satellite array to your computer at your desk, so you don't need to sort of, once you deploy the gear, you can just sit back and relax and watch the data chug into your computer. GPS data, a more comprehensive satellite array, of course, 31 in the GPS array, the accuracy of locations down to less than a few meters. The number of locations is really only limited by the power that you have on the tag. Every second, or less than every second, you can get a location if you want to. And GPS tags either come in data logging forms or in data transmitting forms. So you can transmit GPS data through the Argos system, as well as logging it into your tag and retrieving the log at a later date after the deployment. And then the third approach to acquiring tracking data from birds, GLS, geolocation sensing data, or geolocation data. A very simple tag, just has a bit of memory, a bit of battery, a light sensor and a clock. And it only provides you with 2 locations every 24 hours. Relatively low resolution, obviously temporarily. 2 locations per day is far less than for the other 2 methods. And the accuracy is only about plus or minus 150 kilometers, both latitudinally and longitudinally, so not particularly accurate. But they are cheap, and they're perfectly adequate for trying to understand relatively large-scale movements of birds. Migration scale movements and distributions of a large scale is perfect for that. They're a data logging tag, of course, so you have to retrieve the tag to get the data out of it. So those are the 3 different types of data that we were dealing with. I'm really only going to be talking about the GLS data today, but we do have satellite data, GPS data from birds as well, at least for some of those species. So just a slide to illustrate what those tags look like deployed on a bird. This is actually not one of our study species. This is Salvin's albatross. These photos were taken at the Bounty Islands towards the end of last year. So top left, you've got a GPS transmitting tag. Those panels on the top of the tag there are solar panels. So that tag theoretically would keep on transmitting GPS locations as long as the tag remained on the bird and remained charged. That tag's been attached with tape and cable ties and a little bit of glue. And eventually, when those feathers that the tag's attached to are molted and replaced, the tag will drop off, or the bird sometimes preens the tag off if it gets a bit annoying. On the bottom left, you've got a different sort of GPS transmitting tag. You can see the antenna sticking out there from the back of the bird. Again, just attached with tape. And the bird standing up on its nest pedestal on the right-hand side is wearing, if there's eagle-eyed amongst you will spot, it's got 2 leg bands on its right leg. The left leg, as we're looking at it, it's got a coloured identification band. On the right leg, as we look, the bird's left leg, it's got a metal ID band, and attached to that metal ID band is the geolocation tag. So that's a very small tag. Typically now they're a couple of grams, even less for really small species. That would stay on there, or could stay on there indefinitely, of course, attached to that metal band. Typically, those tags are deployed for about a year, maybe 2 years. The bird obviously comes back to the same place to breed, and the tag's retrieved and the data are downloaded. So that's a bit of a crash course in tracking data. So here are some of the results. I'm going to talk just about 2 of the species that we're working on, greater-than albatross. That's one of those species that breeds, in New Zealand at least, only on Campbell Island. It does breed elsewhere around the world. And I'll talk also about southern Buller's albatross as well. But first of all, these are outputs from the RES modelling for greater-than albatross. So this is the probability plot, if you like. So what you're looking at the top panel is a sort of a global predicted distribution for greater-than albatross based on sea surface temperature, distance to land, and bathymetry. And what we know from the literature about where greater-than albatross like to go in terms of those 3 different environmental characteristics. And then I just zoomed in to New Zealand down there in the larger sort of insert plot. And what this plot kind of shows, well, it shows several things. First of all, on that top panel, ignore all that red colour up in the northern hemisphere. This species doesn't go to the northern hemisphere at all. It's entirely limited to the southern hemisphere. The model is just picking out those similar bits of the marine environment in the north which mirror those in the south in terms of those 3 conditions, those 3 environmental characteristics. But if you focus on the southern part of that plot, down in this part of the world, you can see that it's predicting a band of distributions round about 40 to 50 degrees south all the way around the planet. And around New Zealand, the model's predicting that this species really occurs to the south of the main islands, subantarctic species pretty much. If we compare those, I'll there's a slide coming up which compares these side by side, but I'll just go through each of the methods one by one individually to begin with. So the same species. So these are the sightings data that have just been, these plots are essentially sort of density plots, if you will, of those sightings data. So underpinning these plots are individual sightings of grey-headed albatrosses made by members of the public, scientists around the world. And what the top plot shows is that the sightings really predict a distribution around the breeding sites for this species. There aren't many sightings far from land. It's not perhaps surprising given where the species occurs. And if we zoom in down towards New Zealand, the hotspots, if you like, of distribution based on sightings data are really focused around the breeding site. So that right-hand red blob to the south of New Zealand is really centred on Campbell Island. The red blob to the left of that is focused on Macquarie Island, which is another breeding site for this species. And the models also, or the sightings data, we're also coming up with a bunch of sightings around Australia, which may or may not be, there might be some ID issues there, but nevertheless, that's what the sighting information is telling us. And then finally for the species, the geolocation data. So the top plot there confirms that point about this species being confined to the southern hemisphere. And you'll notice that as far as the geolocation data show, in this sort of density plot of distribution for this species, there's some kind of striking similarities between that sort of linear distribution at a sort of 50 to 40 degrees south band around the southern hemisphere. And zooming into New Zealand, most of the distribution is south of New Zealand again, with a big sort of tail of distribution heading off there towards the east. So just focusing on this part of the world for those three different approaches, I think it would be fair to say that there looks like there's some reasonable large-scale agreement between the RES modelling approach and the geolocation data, which is kind of encouraging given that the RES model, remember, doesn't include any location information at all, and that's only based on 3 environmental variables. Ideally, you would have as many as you possibly could have to inform that model, to make that model more resolved. As some of you might have noticed actually on the RES model, there's a bit of a sort of a quirky out-of-step thing happening at the 180 line. I'm not quite sure whether that's a 3D, 2D thing. I'm not quite sure why that's happening, but we're going to resolve that. So that sort of vertical line in the distribution there on the RES model at 180. But also, it's probably worth pointing out for grey-headed albatross at least, that there's not much evidence from the geolocation data that birds head across to Australia. So those blobs around the Australian, Tasmania and the southeast corner of Australia may or not be grey-headed albatrosses. And then a similar set of plots for southern bullous albatross. So again, on the top plot of global distribution, RES modelling predicting where southern bullous albatross occurs. Again, this is not a northern species, so the model is simply just mirroring those environmental conditions north and south. This is a species that can be found very, very close to shore. Not true for grey-headed albatross. Grey-headed albatross very rarely come within sight of land unless they're breeding, whereas bullous albatross, you can find them in Bluff Harbour when they're breeding in New Zealand most days of the week. They're not too far from the coast on many occasions, and so the distribution here is slightly different. Again, it's interesting that on that southern part of the plot, on the plot around New Zealand, we have that coastal distribution. You'll notice that there's a large distribution or predicted distribution going across towards South America, which will tie in with the geolocation data later. And then the sightings data, again, Australian focus and New Zealand focus, not surprisingly. And also, interestingly, sightings of this species off the coast of South America. And when we compare those data with the geolocation data, you'll see from the top plot that really this species has 2 sort of areas of focus. It's, as a breeding species, it occurs obviously around New Zealand and extends its distribution across to Australia, around Tasmania. And that distribution of South America is of birds which are finished breeding, and when they finish breeding they migrate across the Pacific Ocean and spend their non-breeding period 2 or 3 months of the year off South America before flying all the way back to New Zealand to start the next breeding site. So you take those three approaches side by side for Buller's albatross. Again, there's reasonable large-scale agreement across all three different methods, which is, again, kind of encouraging, really, at this scale. There is obviously some quirky anomalies between those three, but in particular the geolocation approach, which is where we know the birds have definitely been, and the RES modelling approach, which is where the predictive model is trying to explain, without any distribution data, where the birds might occur. There's reasonable concurrence between those two approaches. And so finally, just a few conclusions. So again, at large scales, relatively large scales, there's reasonable agreement in the distributions across these three approaches. Now, that's notwithstanding the fact that the sightings data are a bit patchy, they're submitted in an ad hoc way, it's not structured at all. And it's also noting that the RES model, as I mentioned before, is really only using 3 environmental predictors. If we had access to better information that would allow us to use more environmental predictors, the RES modelling would become a lot more resolved. But nevertheless, it's probably fair to say that there's potential for the RES approach to provide useful indicative distribution information for species that are infrequently sighted or with limited or no tracking information. So there are a whole bunch of seabirds that you rarely see from land, and in fact you rarely see them from ships as well. Often only seen when they come back to land to breed. So for those sorts of species, or for species which have got limited or no tracking information, this approach has got some potential, I would suspect. Nevertheless, the RES approach doesn't allow you to resolve things particularly well temporally. We've approached this really only using 2 temporal windows, breeding season and non-breeding season. I was showing you information there from the breeding season, but going beyond those 2 fairly broad temporal windows is difficult for RES. And it has to be said that those environmental relationships between environmental characteristics you choose or think might be important in determining seabird distributions and the seabirds themselves are generally unknown. So that is an issue. And also the fact that seabirds, the dynamism of seabirds does make them problematic in any of this sort of work. And because they range over such large distances, there's very often a scale mismatch between the birds' distribution and the areas of interest for applications to undertake activities in the marine environment. The second of those 2 things, the areas that are being where activities are likely to take place, operate at a much smaller spatial scale than the distribution or the range of a large number of seabirds. So that mismatch has caused all sorts of problems. And even for species with relatively restricted distribution, so these are species like penguins or shags, which are relatively poor flyers, or in the case of penguins, non-flying birds. For RES to be valid, those relationships between the environmental drivers and how seabirds respond to those particular environmental characteristics would need to be well understood. Once you reduce that scale down to species which don't operate over large spatial scales, but which operate at relatively small spatial scales, the need for those relationships to be better understood becomes even more important. And one conclusion that isn't on there, but goes back to the original question around why we started this project, which was whether we could improve upon at-sea surveys. And so if you want to know about what seabirds or which seabirds occur in a particular space in the ocean and how that changes over time, there really is only one way to do that currently, and that is to go out there in a boat and to see which species of birds occur, how many there are, how that changes over time in a structured, repeated way. If you track birds from a particular site, of course, there's no guarantee they're going to go to the site of interest, and a lot more species of seabirds might turn up at any given site that you could possibly track. So tracking really isn't the answer to address that question. And RES might give you some insight in a very general sense about what species could occur there, but to nail that right down to which species definitely occur there and how that occurrence changes temporally, You still need to go out there in a boat, do the hard work, which is a bit of a challenge. Yeah, so at that point, I think I'll leave it there, and happy to ask any questions.
Yeah. Lovely. I just want to say thank you very much, David. That was great. Really nice overview and beautiful pictures and images, which is always gorgeous to see as well. So we'll open up the floor to questions, as I said at the beginning, but I think we had a couple of people that came in late and might have missed. It would be great if you could submit questions via the chat, which is one of the icons at the bottom of the screen. This is because we sometimes have feedback issues if we try and unmute you and use your microphone. So yeah, if you have a question, please send it in on the chat and I'll read it out, and then we can let David loose. So thank you. Come back. All right. Sarah, do you have any?
I was wondering how easy it would be to just merge some or input some of the tracking data information into the relative environmental suitability model, so that you can actually sort of inform it a little and drive it with known information of where the birds have been located.
Just repeat that for
Yeah, so the question from the room was whether we could use tracking data as a source of information to better inform the RAS modelling. And we did think about doing that. The problem with that, of course, is it becomes really quite circular, because you're using tracking data to say, which gives you information about where the birds go. And if you just, and then what happens, of course, you're just cycling around, basically. Yeah. So we've tended to steer clear of using tracking data to gather information about the environmental parameters and characteristics that we can use to inform the RAS model. And in fact, the RAS modelling approach, in order to validate that, we've kind of validated it against the sightings data, and also against the tracking data. One of these three approaches you have to believe to be the truth, which is kind of a weird kind of thing. And so we've made the assumption that the tracking data are the truth, because we know the species that were tracked, and we know where they've gone, because the tracking tags have told us where they've gone. Everything else is up for grabs, really. I'm not trying to question the validity of the sightings data, but we definitely know that those tracking data provide definitive information about where the birds go. So we're comparing, in particular, the RAS modelling approach with those other two forms of information, which are quite separate. And there is a problem also. I'll just get one more slide, which kind of illustrates some of the challenges with this sort of work. So at the same sort of scale, this is Buller's albatross GPS data across a number of years, males and females, over a period of the breeding season. So not the entire breeding season, but a reasonable chunk of the breeding season. And that's their distribution. Now you can model those data. Those data are very accurate. They're GPS data. They definitely go to that place, down to the southwest of New Zealand. If you could model those data and predict where the bird would go, and it would tell you it would go as much further, because the environmental characteristics from that space occur elsewhere around New Zealand. But we know they only go there, and we're confident they only go there at that time. So you have this challenge really with like predictive modelling existing data to tell you where a bird might go when you know with some confidence that it doesn't go where the model's telling you. So there are challenges in sort of linking together those different forms of data and making valid comparisons between them.
We've got a couple of questions on the chat from Elise Smith. I have an interest in little blue penguins. Tulamina. God, I should have thought that up before I said it. There are a few more records in iNaturalist than in eBird. How do you envisage that in the future we'll be able to have amalgamated data?
Well, that would be great. How that would happen is kind of beyond my expertise, but it would require the holders of those two databases to start to talk to each other and get those databases to link together. And it seems to me to be an entirely sensible idea to have. If you want to know where little penguins occur, you should have all the data in one place. Okay. Just more efficient.
From Diane Diniz, where did you tag the birds that were tracked?
Good question. So those 5 species, taking them in turn, sooty shearwaters, they were tracked mostly from the snares, also from Codfish Island, Whenehau, which is off Stewart Island, and then a small number off Mana Island off the west coast, just north of Wellington here. White-capped albatross, they were all tracked from the Orkney Islands, Campbell albatross, not surprisingly, all from Campbell Island. Likewise for grey-headed albatross, and for southern Buller's albatross, all tracked from the snares, which is plot on the screen now.
Thank you. From Robert Chickard, how would you integrate the data of various species in the document to be provided to regulators?
Yeah, so if you extended this approach, if you extended the RES approach further and included more species, you would have to combine those in some sort of species density hotspot type approach. So rather than having a distribution which was going from blue to red for one species, it would go from blue to red for a number of species. So that would just form, each of those individual species distributions would form an individual layer in an overall amalgamated seabird distribution layer or predicted distribution layer. So that could be done, yeah.
From Susan Jackson, how will this information be made available to practitioners wanting to understand the effects of particular proposals on seabirds?
Okay, so our plan really is to obviously write up this work as publication. We can write it up as a sort of a step-by-step approach, toolkit, if you like, for people who need to make decisions to see if it would be suitable for their needs. Now, there would be some caveats attached to it. You know, as I mentioned, it's not going to give you the sort of resolution of information you might necessarily want, but you'd only know that if you sort of scratch the surface and sort of see how the results panned out. But that could be done. We could make it available in a form that would be digestible and meaningful for people who needed to use it in a practical sense.
Okay. Next one is from Ted Howard, which is we need to put the predator data into your modelling data.
Predator data. Okay. Yeah, we could. I'm not quite sure how to answer that. So seabirds at sea have very few natural predators. Once they leave land, when they're not breeding or when they're foraging over the sea, they don't really have many predators. A few of them get eaten by sharks, but they really, their survival is really quite high. You can expect them to survive sort of 95, 96% from one year to the next. So I'm not quite sure about that one.
Okay. Just a quick apologies to everyone that's now looking at the room instead of David. I suspect it's because my voice is very loud. And from Rob Shuckard again, how is your important parameter for RES seawater temperature impacted by rapid changes that may change their feeding behaviour?
Yeah, so that's a really good question. So this all comes down to scale again, and both in terms of space and also time. So the way we've approached this is we can't account for those very rapid, small, relatively localised changes in temperature. You would need to constrain your approach to a scale that had that sort of level of fluctuation, both in terms of space and time, to be able to do that. For the species that we're looking at, that kind of gets lost in the noise, and we've averaged things out over large temporal and spatial scales in order to look at those large scale distributions. But again, from the RES approach, you would need to understand in great detail precisely how birds responded to those particular temperatures, and it's not at a large scale it becomes more or less indirect, whereas a small scale a more direct response from those direct relationships, not just for the sea surface temperature or sea temperature generally, but what it is about those changes in temperature, how that affects components of the marine system, becomes more important. Understanding those relationships becomes more important. So that it does get a little bit tricky. That RES approach, I think, would get very tricky at small spatial scales.
Okay.
And temporal scales.
Thank you. I'm going to give you my chair so that people can see you. Please come here. And one more from Ted Howard, which is, have you done any multimodal modelling to differentiate between breeding and non-breeding behaviours? We noticed that there seems to be significant for Hutton shearwater. Breeding birds seem to range further when feeding chicks, or Amaru to Cook Strait and out beyond mono land predators to breeding populations.
Yeah, so we've only done modelling at two modes, so it's kind of multimodal, but not quite as multimodal as possible. So as I mentioned before, we've only split our RES approach into the other approaches that followed on from this. They've only split into breeding and non-breeding, and so that changes by species, of course. It also differs across species in terms of what birds are doing when during the calendar year. In theory, again, all of that stuff could be done. You could break the annual cycle down into as smaller components as you possibly could. It's tractable for some of those data sets that we have. It becomes very hard for the RAS. The sightings data could be done by that, but then the number of sightings at particular times of year just drop right away. And for the tracking data, that could also be done. You could split the tracking data into chunks of sizes of boxes, whatever choosing you chose, really. It's not that tricky. So the problem that we would have, the approach that we've adopted, which is basically a comparative approach across those 3 different methods, is having the ability to compare those approaches validly, having truncated or boxed things up into smaller and smaller compartments. So we've started at quite a large scale, both temporally and spatially, but there is potential for it to be reduced down. I don't think for us it's going to be particularly easy for the species that we've been working on, for which we've got tracking data, to go much below breeding season and non-breeding season, but I could be wrong.
Well, I think that was our last question and a really good place to leave it. So I'll just say thank you again to David. Kia ora. We appreciated it. And thank you to everybody who came today and gave us your questions. Please join us next time. We'll be promoting the new webinar very soon. You can sign up to our e-newsletter or follow us on Twitter. And we've also, if you're based in Auckland, have an event at the Maritime Museum on the 19th of August with Ben Knight and real-time forecasting and what that will mean for aquaculture and safer beach access. So thank you, David, again. Thanks, everyone.